Let's walk through the different scenarios of integrating sine to the n power of x times cosine to the m power of x dx. Here, n and m are whole numbers greater than or equal to 1. The strategy we use depends on whether the powers of sine and cosine are odd or even. There are 4 main cases we want to consider: sine odd and cosine even, sine even and cosine odd, both powers odd, both powers even. Let's look at each case. First, suppose n is odd and m is even. Consider the integral of sine to the 5th power x times cosine to the 2nd power x dx. Since the sine power is odd, I want to save one copy of sine of x and put it to the side, and I want to rewrite the rest using the identity sine squared of x equals 1 minus cosine squared of x. So I rewrite sine to the 5th power of x as sine to the 4th power of x times sine x, where I'm putting one sine x to the side. Then we rewrite sine to the 4th power of x as the quantity of sine squared x squared. Now we can replace sine squared of x with 1 minus cosine squared of x, which gives us the quantity of 1 minus cosine squared of x squared. This becomes the integral of the quantity of 1 minus cosine squared of x squared times cosine squared of x times sine of x dx. We've set this up now to use u-substitution. And in these problems where we put one sine of the x to the side and then convert everything to cosine of x, we let u equal cosine of x. Taking the derivative of both sides, we get du dx equals negative sine of x. Multiplying both sides by dx, we get du equals negative sine dx. This then gives us, if we divide by negative 1, negative du equals sine of x dx. Now we can do the substitution. We replace cosine of x with u everywhere, and we replace sine of x dx with negative du. We can pull the negative out front, and so now we have the negative integral of the quantity of 1 minus u squared squared times u squared du. From here, we can just expand and integrate like a polynomial. The quantity of 1 minus u squared squared is 1 minus 2u squared plus u to the 4th power. Multiplying by the u squared that's left over gives us u squared minus 2u to the 4th plus u to the 6th. Our integral is now the negative integral of u squared minus 2u to the 4th plus u to the 6th du. We bring our negative down and we integrate term by term. So we get u to the 3rd over 3 minus 2u to the 5th over 5 plus u to the 7th over 7 using the power rule of integration. Now, since this is an indefinite integral, we're going to put a plus c at the end here. Distribute the negative in and substitute cosine of x back in for u, and we get negative cosine to the 3rd of x over 3 plus 2 cosine to the 5th power of x over 5 minus cosine to the 7th power of x over 7 plus c. The key idea in this first case is, if the sine power is odd, save one sine of x, put it to the side, convert the rest of the sine powers into cosines, and use u equals cosine of x to do u substitution. Now let's look at the second case. Suppose the power of cosine is odd and the power of sine is even. For example, consider the integral of sine to the 4th power of x times cosine to the 3rd power of x dx. Since the cosine power is odd, I want to save one copy of cosine of x and put it to the side, and rewrite the rest of the cosine powers using the identity cosine squared of x equals 1 minus sine squared of x. So cosine to the 3rd power of x becomes cosine squared of x times cosine of x. We then replace cosine squared of x with 1 minus sine squared of x. We get the integral of sine to the 4th power of x times the quantity of 1 minus sine squared of x times cosine of x dx. Now we use u substitution. This time we let u equal sine of x, then du over dx equals cosine of x, so du equals cosine of x dx, which now we can do the u substitution. We replace sine of x with u and cosine x dx with du. We get the integral of u to the 4th power times the quantity 1 minus u squared du. Now distribute the u to the 4th power and we get u to the 4th power minus u to the 6th power du. So we have the integral of u to the 4th power minus u to the 6th power du. This gives us u to the 5th divided by 5 minus u to the 7th over 7 plus c, using the power rule for integration. Substituting sine of x back in for u, we get sine to the 5th power of x over 5 minus sine to the 7th power of x over 7 plus c. So in the second case, if the cosine power is odd, save one cosine to the side, convert the rest of the cosine powers into sines, and use u equals sine of x to do u substitution. Now, what if both powers are odd? If both powers are odd, then either of the previous two methods will work. Suppose we have the integral of sine to the 3rd power x times cosine to the 3rd power x dx. Since both powers are odd, we could either put one sine of x or one cosine of x to the side and then do the same thing for u substitution. So in this example, let's save one cosine of x and put it to the side. So we rewrite cosine to the 3rd power of x as cosine squared of x times cosine of x. Then we replace cosine squared of x with 1 minus sine squared of x. We now are going to calculate the integral of sine to the 3rd power of x times the quantity 1 minus sine squared of x times cosine of x dx. Let u equals sine of x, then du equals cosine of x dx. We substitute sine of x with u and cosine of x dx with du, and now we have the integral of u to the 3rd power times the quantity of 1 minus u squared du. Distributing u to the 3rd power, we get u to the 3rd power minus u to the 5th power du. Integrating with the power rule, we get u to the 4th over 4 minus u to the 6 over 6 plus c. Substitute sine of x back in for u, and we get sine to the 4th power of x over 4 minus sine to the 6th power of x over 6 plus c. So when both powers are odd, just pick one of the odd powers to save a single trig factor from, convert the rest using the Pythagorean identity, and use u substitution. Finally, what happens if both powers are even? What we did earlier in the other scenarios will not work directly here because we can't really just pull a single sine of x or cosine of x to the side to pair with d of x and then do u substitution. When both powers are even, we can use power reduction identities. The two identities we use are sine squared of x is equal to the quantity 1 minus cosine of 2x all divided by 2, and cosine squared of x is equal to the quantity of 1 plus cosine of 2x all divided by 2. We'll put these to the side for now. Let's work with the integral of sine squared of x times cosine squared of x dx. Since both powers are even, we can replace sine squared of x and cosine squared of x using our power reduction identities. Replacing sine squared of x and cosine squared of x, we get the integral of the quantity 1 minus cosine of 2x all over 2 times the quantity 1 plus cosine of 2x all divided by 2 dx. Multiplying the denominators gives us 4 in the denominator, so we can move that 1 over 4 out in front of the integral. We now have 1/4 times the integral of the quantity 1 minus cosine of 2x times the quantity 1 plus cosine of 2x dx. This form here, we have 1 minus cosine of 2x times 1 plus cosine of 2x, is the factored form of the difference of squares. So we can replace this with 1 minus cosine squared of 2x. This now gives us 1/4 times the integral of 1 minus cosine squared of 2x dx. What do you notice? Cosine squared of 2x still has an even power, so we can use the power reduction identity again. Cosine squared of 2x is equal to 1 plus cosine of 4x all divided by 2. Substituting that in, we now have 1/4 times the integral of 1 minus the quantity 1 plus cosine of 4x all divided by 2 dx. We can simplify the inside and write 1 as 2 over 2, which then gives us 2 minus 1 plus cosine of 4x all over 2. This then gives us 1 minus cosine of 4x all over 2. We bring the 1/2 out front and multiply it by the 1/4, and we get 1/8 the integral of 1 minus cosine of 4x dx. We can break this into two integrals, and we know that the integral of 1 dx is just x. And the integral of cosine of 4x, you can think of this as another quick u substitution. Here we have 4x inside a cosine, so we let u equal 4x. Then du over dx equals 4, so du equals 4 dx. Dividing by 4 on both sides, we get du over 4 equals dx. We can replace dx with 1 over 4 du, or du over 4. So the integral of cosine of 4x dx becomes the integral of cosine of u du over 4. The integral is then sine of u over 4. Substituting 4x back in for u, the integral of cosine of 4x is sine of 4x all over 4. So inside the brackets, we get x minus sine of 4x over 4. Let's not forget the 1/8 we had out in front of our integral, so we can distribute that in. We get x over 8 minus sine of 4x over 32. And then we add c because this is an indefinite integral. So when both powers are even, the main idea is to use power reduction identities until the expression becomes easier to integrate. So let's summarize this whole video. We were working with integrals of the form sine to the n power of x times cosine to the m power of x dx. If n is odd and m is even, save one sine of x, convert the rest of the sine powers into cosines, and use u equals cosine of x to do u substitution. If n is even and m is odd, save one cosine of x to the side, convert the rest of the cosine powers into sines, and use u equals sine of x to do u substitution. If both powers are odd, then either of the odd power methods will work. If both powers are even, we use power reduction identities to reduce the power to make it easier to integrate. Ultimately, check your exponents first. Once you know whether the powers are odd or even, the strategy kind of becomes pretty clear. If you found this video helpful, consider subscribing, commenting, or liking the video to support the channel. I'm Joe, and thanks for spending some time with me.